The next speaker is AUTOSAR, who along with others co-founded CUBIC in 2007, I believe, and we all know and love the idea behind airline. There's hardly a functional programming language community that has not tried to report various good ideas for quick check to them. CUBIC is a company that is based on taking the ideas behind quick check and putting them into practice in the world, and we're going to hear a little bit about putting that into practice in a particularly thorny part of the world, which is the automotive world. So, without further ado.
Thank you for the introduction. And indeed, so John and I, we started Quick Check, selling Quick Check a few years ago. And we sold it basically as the first customer to Ericsson. Right? They were using airlines, so that was a nice match. We programmed Quick Check in airline because that would fit them well instead of using the Haskell version. So we had the market, we had the tool, and they were using it. And strangely enough, they were the first paying part of Ericsson, the first gave it away. The first paying part of Ericsson was the radio base station department. As you all know, radio base stations are those things you connect your mobile phone to. And those stations are programmed to C. Right? And they were the first commercial customers for airline Quick Check. Why is that? Because all the testing of those radio base stations was done on airline. So they had the department in Linköping, the people department, but they were constantly writing wrappers between C and airlines if their testing would be easy, and they did the testing in airline. And one way that Mike Williams always said, Mike Williams was one of the founders of airline, he said, well, the best way to get a new, or getting an airline into the department of Ericsson is through testing, because that's not harmful. I mean, you don't touch the development, but testing, that's okay. You can do it in any language. Even TDC3 is used for testing, so come on, you can use whatever you like. So we started there, and then we got more and more customers all over the world. Somehow we wanted even more customers, but hey, then we have to start departments like in Linköping to make the transition and make a nice airline framework, etc. And then we had this fantastic guy working for a school for Noel, which said, oh, but we can do that automatically. So you can read C code, parse it, get all the type of information, write all the Martian code automatically, and then just talk to C from an airline shell as if it is C itself. So he did that as a kind of project, and we were very happy with it. And we said, well, let's try it on something, and that's where this starts. We tried a master thesis in automotive industry. Said, let's look whether we can test real C software. And since we are based in Gothenburg, and lots of car companies around, let's look at car software. That's as much C code as you can get. It's not C++, it's real C, so that's still rather easy. Let's do that. So we put a master thesis on that one, and then after a few weeks, we got some real attention there. Not only from the company that makes the software for the car, but also the car company itself was really interested. And it's because they had a problem. And it's always nice to have a problem, because that means you have business, right? So this is a car. For those of you who would recognize the model, it has nothing to do with the car company we work for. In the car are computers. They are called ECUs in car terminology. And there are about, in a kind of fancy car, 63 computers or 65 or something like that, spread around over the car. All those small computers, they steer the brakes, or your steering wheel, or your air conditioning, or your windows, or whatever. They're all kinds of computers. And all those computers talk to each other. It might be useful for the brakes to know how fast you drive, for example. Right? That makes sense for the brakes to know. So the motor can be told to send some information to the brakes. But the brakes can also tell the motor, hey, now we're braking, it should probably not continue kind of burning a lot of energy. So that kind of things is happening in the car. Typically, a car company would buy all those boxes from different vendors. Right? They would go to, typically in Europe, you have this big one, Bosch, more worldwide, Continental. You would go there and you would buy a few of those boxes, like the brakes and the gearbox, and then you would go to another one, you buy the steering wheel and the airbag and another one for the windows, etc. And you put those all in the car, and then you hope it works. And one of the big questions then is the software in all those boxes, is that compatible? The guys making those boxes, they basically not software guys, they are hardware guys. They do a perfect job in hardware, but they don't normally make the software themselves. So there are some software houses making the software for them. Right? That's what they call tier 2 stand in the terminology of the car companies. So you have companies making software and put that into a box, and then the box goes into the car. So there's two different ways of solving that problem of compatibility. One, very, well, probably the best known way of doing this is to say, well, make sure that all the boxes we buy have the same software. Then the likelihood that those boxes talk to each other in a nice way is very high. Right? And you, more important than that it works well, you know who to blame if it doesn't work. That's extremely important in our industry, knowing who to blame. So you just ask one supplier to make the software for all the boxes, and then you do it. There's a slight problem there in that business model, is that the guys making the boxes says, yeah, but if you put our software in, it's much cheaper. So if you want to buy one with that software in, hey, that's more expensive. Now we can earn money, right? And we work together with a Chinese car company based in Sweden, which is not so rich and it was going very, very badly. And they couldn't afford to actually get into that market strategy. They couldn't afford to say, we depend on one company and the price would go up and the boxes would be more expensive. So they said to us, when we were doing this testing, said, well, there must be some other way of doing it. Can you not ensure that the software is compatible? Right? How do you normally ensure that software is compatible? Well, you define a standard. And that's of course what the car companies did. So in order to get compatibility, you have a standard. It's like when you buy a new printer, right? You just connect it to your home network and everything works and the computer can print. That's because it's based on the standard. And when you buy a new router, all your computers talk to the router. You have no installation problems whatsoever. You put the router there, all your computers work immediately with that router. That's standards. So you standardize and problem solve. And that's what they did. And then the next question then becomes, okay, there's a nice standard. This standard we look at is called AUTOSAR. It's a European standard, I would say, because it's mostly used in Europe, but also Ford and Toyota, etc. are partners in that standardization body. And they all together define what the software in the car should look like. And the only thing you then have to do is say, does the software conform to the standard? Because we know that if the software conforms to the standard, then it will work. So that's fine. And this is a much more practical question for us, because that can probably be solved. I mean, the other one saying that is the software compatible in the different ECUs, you need the ECUs together. That's hardware, we don't want to get into this, but hey, this is a nice problem. So, software conformance. Anyone knows how to do that? Well, in industry you know perfectly well how to do that. It's very simple. You test. You test for conformance. And how do you test? Testing is called outsourcing. So you outsource that to India, and then everything is solved. So that's what they did. This consortium has some money, there's a lot of car companies involved. They said, let's just buy a few hours from it. In India, they are cheap anyway, so they bought 30+ person years, and said, make some test cases. And then this test suite will be used as the conformance test suite. And everyone has to run that test suite, and then we know it's conformed. Took a bit more time than I had expected actually, but hey, it's a difficult standard. It's actually one of those really good standards, as far as I've seen. It's still full of bugs in that sense and ambiguities, etc. But much, much better than most standards I've seen in the telecom industry. So it's kind of a good standard, nothing wrong with that. But nevertheless, it was a complete disaster. Such a disaster that after putting all this money in there, which probably is not much for car companies, but much for me, after that they said, well, we don't use those test cases. It's not good for us. So they had 30 men here put in making the test case, and then they just throw them away. And one could wonder, why is that? Why didn't that work? It's not because the Indians didn't write good test cases, but I will try to explain why they did not work. So AUTOSAR is a standard defined by a consortium. And as in any standard defined by a consortium, everyone there wants to have certain things in there. For political reasons, for technical reasons, or for completely irrelevant reasons. But they want to have their stuff in there. So the result of this standard is that it's completely configurable. There are thousands, really, of parameters you can specify. boxes in the car. And from there they say, well, then therefore we need those messages on the CAN bus, counts one of the protocols, and those on the FlexRay bus, and those messages on the LIN bus, etc. So they make a big model of the car, you could say, but they don't want to specify the details. Then someone comes in with a configuration tool, and from this big picture of how the car should look like, they take the relevant bits here, and they make an XML configuration, which is 60,000 lines of code or something like that, a small XML file. Because XML is always more bulky than it should be. And then you do from there, you do your code generation, and this is what the vendors do then, and they create a library, a C library, a lib file, and some header files, and they ship that to the ECU builder, and they put it in the box. So important to notice that you have to do this configuration tool thing always, because the standard says you may add some vendor-specific things in the XML code. And in order to get the code generation work, you better do put some vendor-specific things in the XML code. So whenever you want to do this, you have to have a configuration tool as well. That's good for the vendors because they can sell a combination of code generation tool and configuration tool together, making one game. But that's awesome. So what is a test? A test then is both the configuration and the set of API calls to do in that situation, that configuration. So you can't just say the test is, well, you do this and this and this. You have to say you do this and this and this in the context of this configuration. And that's important to realize. So if you then have to design a test, what do? You're not going to write 60,000 lines of XML code, because then the test gets too big. So you say, let's take a small configuration and a small number of API sequences per configuration, because that's doable. You wouldn't be able to make this enormous large configuration for every test case. You have to do it small. But then you are smart, of course, because you take a small configuration. In this configuration, that's a tricky test case. So let's test that. And in that configuration, that should be tested. The problem with that is that then, of course, if you ship those test cases, the vendors have to change the configuration slightly to make the code generation work. So they still have to do some manual stuff to get the code generation running. There are actually companies in automating this process as well. So there's some work that will be done with vendors. So let's do a little bit of mathematics. What can you possibly expect from someone in India to do in a week's time? Well, probably you can come up with 2 configurations and say 3 test cases or 4 test cases around such configuration. In a week, I would not be able to do that. But hey, in India they're very effective, they work with lots of hours, so this would probably be possible in 1 week. And I think it is possible because if you look at what they produce per week, then it's about this, with 30 people. That's about what they do. There's probably a lot of copy and pasting in it as well, but this is what you produce in 1 week. And then you multiply that by 15, and not that much holiday in India, and you get about what they produced in 30 men. So you get this as a vendor that has to test the software. You are told by any brand, BMW or Volkswagen or whatever, that okay, you implemented the software, show us that those test cases are actually running for your software. You say. Then we have to make all these configurations, adapt the configuration, run those tests, adapt that configuration, run those tests, etc. That will take a little time. We will be back to you in a few weeks, right? So that's really a lot of work to just run those test cases. But that's not the worst case. The worst case is that you actually have to find out for those test cases that do not actually conform to the standard. So there are test cases that fail, but it's not a big problem that they fail because your vendor doesn't use that feature in that configuration. And they're not interested in that. In order to give your car company the best performance, you have to take that out. So that's the real nightmare in all of this. So this is the traditional testing approach, right? You do some kind of module testing. Each module is tested separately because then you can make small configurations. You have a minimum configuration to support your tests, and then a few test cases around. Which means that you basically test 1 or 2 features at a time. We take a different approach. So this is now the approach we do with quick check. So we said, well, if we want to test this, then we do it slightly different. We would do it as follows. We use pitch check, of course, as the motor behind all this testing, and we use models for, in this case, complete components, complete UR, or a CAN stack, or whatever. We get an XML configuration from the company, and we said, okay, this is what you want. Okay, we generate our tests automatically from that configuration. So we're not depending on the configuration. The tests that we generate with QuickCheck are already before the configuration. We still have to send this configuration to the vendor, which has to create code first, and then has to give us the code we test against. And then we run thousands of tests, different tests for that configuration. And one of the things which is new, and they could have done as well in manual testing, is we make one big configuration, really large one, with lots and lots and lots of features in it, such that the vendor only once has to make a code. But we make such a tricky configuration that it actually covers a lot of possible scenarios, which both the vendors and we like a lot, because we don't have to supply lots of different configurations. And we can easily switch configurations, and test will automatically adapt to that configurations. So we test more scenarios and we test more features together, I would say. So in this model-based testing approach, we test the complete clusters. We have one configuration to support all that. We run huge numbers of tests, and all the features are tested at the same time. And then, of course, we use this nice C stuff to automatically talk to the C code. We have to create C stubs on the fly, because there's a lot of, in the standards you can say which C functions you use for a specific event. So the names of the C functions are not set. They are configurable. So you don't know when you write your configuration, well, we put the names in there, but in principle, you can put any name for a function like set an emergency sticker. That could be any name. So you have to know from the configuration which name to use in order to test it. So, okay, so we did this in a small scale first, and then this company came to us and said, can you do this large scale as well? Let's give it a try. We want to make a new car now, and we want to have this tested very well. So we give you 3 clusters. These are the 3 ones. One is the communication stuff, the other one is 2 protocol stacks. We have the implementations for those from vendors that we trust. They have tested this software already, but can't you just use those well-tested things to make models and show us that this is actually plausible, and in particular, how much time is this going to take? And we give you 3 months. Okay, fine. So what we then did is we started creating the models and run them against 3 different vendors. And one thing that the car company was really interested in is if we had deviations in from the different vendors. If different vendors did things in different ways, because they were all classified as being, well, proper implementations. And of course we did. And we had then a discussion with the vendors, and sometimes it was the workers, oh, that's stupid, we have working in. And sometimes they said, yeah, of course we don't follow the standard, it's stupid. You can't do this. Well, one example is, for example, which they all did not do, is if you stop talking in the car, if you kind of switch it off or whatever, they said, well, you shut down the communication and then you can start communication again. It's kind of a restart communication. I'm not sure where it's used exactly, but you can stop the communication and restart the communication. And when restarting the communication, you have a choice. Either you remember what you were sending when you stopped it, so all the buffers are still there, and you just send out the messages. Or you clear all the messages and say, okay, we just forget what we were sending. And in the standard says, oh no, you can stop and restart the communication, and then you should send out all the things you have been sending out before. But no one's doing that, because it's very annoying if you stop the car and you start again, and the car thinks you're still running on the autobahn at 120 kilometers an hour, right? That's not what you want, so you don't follow the standard. But no one really put the effort in changing the standard, because hey, we all know this is nonsense, so why would we do it? We find that kind of things, and then we adapt the model and the standard accordingly. Okay, we wrote 500 pages of, well, every such document is about 500 And such 500-page document results in about 1,500 to 2,000 lines of airline code in the grid check model. If you compare that to the C testing code, where you have written your tests in C, that would be about 50,000 lines. So we gain a factor of 10 in writing a model instead of testing. I know this because the tests were supplied by the vendors as well, so we know what tests they had run, and it's about 50,000 lines. It took us, for one such component, about 12 weeks to make one component. We did 3 components in parallel, about 12 weeks to make such a component, which is fast. And then we found all kinds of errors in the code because of our way of testing. So even though this was very well tested software, we found things because we mixed all the features together in this big configuration. And we could do that because we have a model and we can test things together at the same time. All the assertions are always there, is kind of how we call it. Because you normally in a test you would only write assertions of things you expect to fail. But if you model, you have always all assertions at the same time, which is very powerful. So we found failures in obvious fault-free implementations. There was one implementation which basically said do nothing as a comment. And indeed, you should not do anything there in that part of the code. Nevertheless, it was wrong to do nothing there because the coding style was such that if you do nothing, you fall through, and there's always a return value and you return something. So returning something was not do nothing in that case. All that kind of stuff you find because you're much more mature in testing. So all that kind of things we found. Let's give you a quick bug of things we find which were not found in traditional testing. CAN is a communication protocol. Think of it as IP communication. You have an address space, 11 bits, or an extended CAN in 29 bits. So old version 11 bits was not enough because you only have 2,000 messages, or type of messages. They needed more messages. Let's extend that. So what happens then is that, for example, if you have a brake system which is newer, you would support extended CAN system. And then you can still have the same IDs for the messages, so you could have an extended CAN ID of 113, but that has a higher priority than of a normal standard ID of 140, because the lower the number, the higher priority. So if you want to have a high priority message, you give it the low number, like the brakes. So when you have too many messages, you buffer the messages, and the highest priority message should be sent first. That's the whole idea of the car. It's all real time, and you want some messages to go a bit faster, like the brakes are typical more important. So in this implementation, then in the C code, you have 32 bits in which you store the ID, and in order to remember was it a standard CAN ID or an extended CAN ID, you switch this one on for the extended CAN. And you already guessed what goes wrong, right? We send a message, ID 112, then 113, 114, some buffering has to happen. You can only send one message at the same time, so you buffer those two, and then you do a confirmation, and then what you see is that you send 112, and then 114. So you do not send 113, although it has high priority. Why was that? Well, when they compared the IDs, they didn't clear this bit, and then they have really big numbers there. Right? So this means in a car that when you have a new brake system, an old stereo, and you're fiddling around with the stereo and brake, then the stereo has the priority. Another thing we found is, and this is also purely through this kind of idiocy of just quick set tests, if you stop a group of communication, so you can bundle events in groups and you can stop a group. If you stop a group, then the communication for that group should not continue, right? You stop only that group and all the groups can still communicate. And then we had this nice test case which is hard to read. You do something in group 10, and you put something in, and then you stop group 1, which wasn't even started, but then you stop it. And then you do some writing. And nothing happens, nothing is sent. All the group 10 stuff should still have gone through. But in the middle you stop group 1. And it's completely unrelated group. No one in his right mind wants a test case saying, oh, let's stop group 1 in the middle of something with group 10, right? This is just because Pritchard pure luck puts it in there. And even if you put it in this or that position, it wouldn't help. But if you put it in that position just before you do the round signals, then something happens. Well, the effect is that you stop all the groups at the same time. Because they didn't only clear that bit, they cleared the whole part. So that kind of errors are typically overseen in traditional testing. You find them easily by using quick check. So to conclude, or get to an end, what we did is we modeled the standard. And of course, if we model the standard, we make the same mistakes as when we would implement the standard. And since we don't know anything of car industry and AUTOSAR, we make even more mistakes than any other person would do. But that's not really a problem in our approach, because we have the implementation of 3 vendors which we test against. And we always trust them to be correct, and we are the ones that are wrong. It gets interesting when they all 3 do something different, or at least one of them does something different than the other. Then we definitely have something interesting to tell about the compatibility between the different vendors. So it's not that we are so great in knowing AUTOSAR, we can do the standard much better than they do. No, we follow what they do, but we actually detect inconsistencies between all. So we created lots of 3 clusters. At the moment we are working on many more clusters. They said, oh, if you can do that, you can probably do the rest of the car as well. So work on that. We also, the flexibility is in this configuration. They can give us any configuration we can start testing. So we don't only do this for one car company. We'll in the future be able to do it for many car companies that just have different configurations without much effort from our side. Or we can push a button. And we absolutely outperform the traditional testing in both finding the number of errors, effectiveness, and also efficiency, because it takes much less work. We're now partnering up with the standardization company in Sweden, which stands for all electrical devices and all the other things in order to achieve this, that your car software will be approved by SP whenever the software is correct and passes our check test. That's what I'm saying.
How many people did you have working on that 12-month sprint for the first proof of concept?
Don't say well.
Order of magnitude. I mean, you're talking about billions of persons.
We were 3 people during 3 months, so because we had to power loss. Alan is really nice in that sense because it's easy to find.
Do you have any idea what fraction of the stage space you're covering in your test?
The space is infinite in that sense because you can really do a lot. But of course,
So that's even worse than me then.
I was really impressed by 100% accuracy. You had 1,000 tests on this, but in practice, I guess we are the same, right? But we run more than 1,000 tests. We run actually, well, 24-hour tests, things like that. But what we do is we measure the state space of the model, not of the real car. Right? So the model state space we can test much better because we have control over that. We can see it. And there, it's hard to say how much. It depends a bit on which component we look at. But say 20% or something like that. But it doesn't really mean that those states we have not visited are so much more interesting because it's probably just little data changes that we do not want. But it's a very good